Hello, grade 11s, Mindsetters. It is your chance now. It is our Triple M day, which is Mindsetters Maths Monday. And I'm not alone, I'm with Dina. How are you, Dina?
I'm changing my name to Mina because then we'll make it 4 M's.
All right, it's going to be 4 M's today. It's Mindsetters Maths Monday with Mina. How's that? Let's see if you like it. How are you doing?
I'm doing very well, Abraham, and I'm looking forward to spending some time with the grade 11s on analytical geometry today.
I'm sure they are up and ready because some already, they're writing their exams. So this is going to be a great revision for some.
Absolutely. All the topics that we've covered so far in analytical geometry, we'll be looking at those in examples.
All right, quick tips before we go. As they're preparing for their exams, what would you like them to do?
I would like them to work through as many examples as possible, not to read through any notes, but just to practice examples.
Practice, practice, practice.
Yes.
Thank you very much. Go take your stand.
Thanks.
Right, Mindsetters, there's 4 M's and 3 things that I need to tell you. The first one is that those 4 M's are Mindsetters Maths Monday with Mina today. And also the last 3 things that I need to tell you is that 1, we are on Facebook. You can engage with us, chat with us. As you study, make sure that you have your cell phone next to you. Our Facebook link is facebook.com/learnextra. And that's where you can get also other Mindsetters helping you if you don't understand certain things. And also ask us some questions and we'll reply to you. Secondly, go over Twitter @LearnExtra. I'll be taking some of your tweets and see what are you saying on Twitter as you follow us, and we'll follow you back. And lastly, this show is proudly sponsored by Macmillan. Last week we had a launch, a great one, whereby they were launching their e-learning, and we'll be telling you about those ebooks, how you can get hold of them on the page. I'll be giving you more details. But for today, you can get your notes for free on our website link, which is learnextra.co.za/live. Thank you very much for tuning in, and let's get ready now to learn more Learn Extra. Dina, take your time.
Thank you very much, Abraham. Right, grade 11th, earlier on in the year, we did a little section on analytical geometry, and the notes were posted, the theory notes were posted on the 3 topics that you had already covered in grade 10. And that was the distance of a line segment, the equation of a straight line, and the coordinates of your midpoint. Now, this year, we've introduced a new concept, and that's called inclination. So all the formulae and all the theory notes are uploaded already. You just need to get those. I'm just going to go through briefly some of the things we will be touching on in order to work through examples. Remember earlier on I said the tips for the exams is just to practice worked examples. Don't just read through it and think that you can do it. You must actually physically do the example. Well, we're going to work through 3 examples today and hopefully really extract some of the main important aspects of analytical geometry. So let's get started. As I said earlier, we're going to work through examples, 3 of them, to grasp the major key concepts in analytical geometry. And the fundamental one we would start off with would always be the gradient. And the gradient is defined as the change in y divided by the change in x. So how much is our y values changing with respect to a change in x? And then we've got if we have 2 lines, line 1 and line 2, then if line 1 is parallel to line 2, we'll find that the gradients are equal to each other. And we can conversely use that. If the gradients are the same, then we can conclude that the lines are parallel. And then another very important one is if the lines are perpendicular, then we get that the gradients, the product of the gradients, must be -1. So these 2 concepts we'll be using quite a lot. Then we have the equation of a line, which you learnt about in grade 9, so that hasn't changed. So it's still y equals mx plus c. However, you may have learnt about an alternative one, which is y minus y of a equals the gradient multiplied by x minus x of a, where a is any point on that straight line. Then the distance of a line segment, I said earlier, you have already covered that in grade 10 as well. But the distance, let's say AB, between points A and B, is always going to be the square root of the change in y squared plus the change in x squared. And change in y, change in x is good because your gradient is also a change in y and a change in x. And then finally, the inclination something that you've learned this year, is to integrate we're going to integrate trigonometry and gradient. So if theta is the angle of inclination, then this angle is the angle between the straight line and the x-axis, and the definition is that the tan of that angle will always be equal to the gradient of the line. The properties of geometrical figures we'll be utilizing in the examples we will be doing, so I won't be looking at those. There's quite a lot of figures, there's quite a lot of properties, so it would be too complicated to actually do it at this stage. We'll extract those in our examples. Right, so let's look at the first example. It does come from the maths book by Macmillan, Clever Keeping Maths Simple. Very good example just to get us off the ground. We have a shape, and here's a figure that we were talking about. We've got a shape, and it is a parallelogram. And we've also been given 1, 2, 3, 4 coordinate pairs in the diagram. The diagram's been drawn for us. And just double checking that's in the right quadrant, negative x and a positive y, positive, positive, and then we've got a positive and negative over here. And the first question is, write down the coordinates of E, the midpoint of line AC. So we have point A, we've got point C, and we would like to determine what the coordinates of this point here are. So we're going to look specifically at how to calculate the coordinates of the midpoint. Now, any of these questions around distance and midpoints, we are always going to use a formula. So it's critical that we utilize the correct formula. Now, midpoint we didn't calculate earlier, we didn't actually put it down, but the coordinates of any midpoint are always the sum. And let's just undo that for a little while. So the midpoint is going to be defined as the sum of the coordinates. So whereas the distance and the gradient, it's the change, the y and x will be the sum of those values divided by 2. Okay. So we want the coordinates of this point, which we are going to now add the x coordinates. Negative 3 and 2 gives us negative 1. If we divide by 2, we get negative a half. And the y value would be 6 minus 4 is 2. 2 divided by 2 is 1. So we've got that in the second quadrant, negative a half, 1. So E being the midpoint, it would simply be negative 3 plus 2 divided by 2 and 6 minus 4 divided by 2. You don't have to worry about what coordinate gets written first because we're adding them and dividing by 2. Then we would like to work out the coordinates of D, which is the fourth vertex of the parallelogram. So we now have that this B64, we don't have the coordinates of AB, but we've got E. Now, one of the things that you as a mathematician must really begin doing is that when you are given a particular figure, that in the back of your mind, even if you don't write it all down, you are probing into what the given properties of that figure are. So I haven't put them on because I wanted to see what the questions actually were. But the moment that midpoint is given, we know that something special about the diagonals of a quad is that that becomes equal to that. In other words, this line acts as a scissor and cuts that in half. And it also cuts that in half. So that diagonals actually bisect each other. Because we can fold this figure in half, which means that that line is the same length as that line. And we can fold the parallelogram in half across this diagonal. So it means that that portion is equal to that portion. So the diagonals actually bisect each other. And the bisecting of the diagonals in Euclidean geometry has actually got another meaning, or an alternative meaning within the analytical sense, because the bisection point becomes the midpoint. And we don't actually talk about that midpoint in Euclidean geometry. We just talk that the diagonals bisect each other. So we're actually adding another lens to our Euclidean geometry and beginning to talk about it same property, the point of intersection where the lines cut each other in half, but we're actually giving it almost different terminology. Same thing, but different terminology. So we have that point of intersection. So these yellow segments I've put in there because we know that it's a parallelogram. What else do we know now that we're talking about the properties of the parallelogram? We also know that the opposite sides are parallel by definition. And in Euclidean geometry, we would talk about the opposite sides being the same length. Okay, and while we're doing that, and since that today is a day for revision, just carefully, parallel lines don't have to be the same length. It just so happens that in this figure, they are parallel by definition, and they are also the same length. But a lot of students will say, oh, the lines are parallel, therefore they must be equal in length. Well, I can counter-argue that, and I can say, I can find you a pair of lines that are parallel, but are not equal in length. And if I join the opposite sides, I get a trapezium. Okay, so there are situations in maths where lines that are parallel aren't necessarily equal, in the same way as if lines are equal, they're not necessarily parallel. So I can find an example, equal lengths, make those the same, and they're not parallel. So they could be equal in length and not parallel. So there are some times where these things happen not at the same time, or that can happen at the same time, simultaneously. So here's a good case of showing that that length is the same as that length, and it is also parallel to that length as a definition of a parallelogram. And we also know something about the angles and something about the diagonals. Right, so we are trying to find the coordinates of AB. Now, think about it carefully. This line has got E as the midpoint. I know the end point. I know the midpoint. So I can work out the coordinates of D. And we're going to do that by writing it down here. Let's just go all the way down, and let's just say that what we really have is a situation. We've got E over here. So we've got point E with coordinates -1/2, 1, and we've got point B here with coordinates 6, 4. And we would like to work out what are the coordinates of this point here. And really, we're working with a midpoint, so those two segments are the same. And the best is to always extract the formula for each of the components that you're working with. So for your midpoint, our midpoint E, we actually have that our x of point B plus our x of point D divided by 2, and our y values of B and D divided by 2 actually come to our coordinates of that midpoint, which give me -1/2, 1. Now, in this case, because I have made an equation with the x values and the y values, I can now say that whatever I get there must equal to -1/2, and whatever's in there must equal to 1. So it's almost like working with the inverse of the midpoint. And so I can take just the x values, which is 6 plus x of D divided by 2 must give me -1/2. And now I can solve for x. So I get x of D must be times 2 is -1, and -1 minus 6 is -7. Or, not or, it's not an or set, I'm working out the y values. So it means and my y of B plus y of D as my formula will be equal to 1. And y of B, see what we have it as 4. So we've got 4 plus y of D divided by 2 equals 1, which gives us a y of d as -2. I'm just going to test. If y is -2, then we've got 4 minus 2 divided by 2 is 1. I'm happy. And we'll test the -7. 6 minus 7 is -1, divided by 2 is -1/2. So I'm also happy there. So therefore, D is the point -7. What did we get down here? -2. Okay, so that's using the converse of the midpoint theorem. So we've got that this D here is -7, -2. Okay, then determine the equation of the diagonal AC. Okay, so we've got AC as a diagonal, and we'd like its equation. The moment we have 2 points, we can work out the gradient, and we can find the equation of that line quite straightforward. So I would choose the 2 given points because they are accurate. They've been given to us. So we've got the given information, A and C, and we would like to work out its equation. So we first need y equals mx plus c. Whenever working out the equation of a straight line, we would like to know what its gradient is, and the gradient would just be the change in y over the change in x. That would give us the gradient. And then we could substitute one of these points in order to get c. So let's go and get what that a is. 2, -4. This one is 2, -4. And this one is -3,6. -3,6. So we can substitute in y of a 6 plus 4 over -3 minus 2. So we get 10 over -5, and we get a -2. Would you be happy with that value? Does that satisfy some mathematical intuition? Yes, it's a negative gradient, so at least we know that it must be, in terms of direction, that it's correct. So we now have y equals gradient is -2x plus c, and we now can substitute a point to -4. So we get -4 equals -2 times 2 plus c. And we get c equals, that's -4. So over the side would be 0. And what we're saying is that that diagonal actually goes through the origin. So it's not drawn. Oh, it does. There it is, going through the origin. So the equation of the diagonal is just y equals -2x. Abraham, shall we take a quick break?
Yes, sure.
Good.
Mindsetters, while we're taking that break, you know that we've been telling you about After Earth, a new movie starring by Will Smith and his son Jaden Smith that is coming on the 7th of June in your cinemas. So make sure that you watch this trailer, because after this, it's our competition time. We'll be asking you a question. I'll be giving you basically a code, and that code will be your entry key code to our competition, and you could win double tickets just for you and your friend to come watch out this movie. So make sure that you tune in. Don't go anywhere. After this, I'll also be telling you the winner from last week's Grade 11 show. See you. Welcome back, Mindsetters. You know that's how we roll on our Triple M Day, which is Mindsetters Maths Day. I see a lot of you are enjoying it over Facebook, but I hope also you've enjoyed that trailer. Now, let's get down to business. Our winner for last week's show on Thursday is Stembile Fagude. Congratulations to you. You have won yourself a double ticket for you and your friend to come watch this movie. Stembile Fagude, I'll also be posting on the page. So congratulations to you, Ste. And now, the code for today's show, Grade 11s, is simple. I'm sure that you've heard it from Mina. Mina, you've told them the keyword for today. It is analytical. So yes, Mindsetters, if you just want to win yourself a double ticket for you and your friend to come watch this movie that is coming out on the 7th of June, make sure that you go on lenextra.co.za/After Earth and enter that key code, which is analytical. It's simple, analytical. Let's analyze. It is analytical. So yeah, Dina, Mina.
He's having fun with my name, so I'm going to have fun with his, and I'm going
You
to
know,
do a sort of a reflection of
I'm
his
also
M,
seeing the
and I'm gonna
mindset
say,
is poking you.
Mabram.
The mindsetters are also poking you with that name. They love it though. It's cool.
Good stuff. I will not mean a moo in the studio though. Okay, right. Everybody, we left off where we were working with the equation of a line. The last two questions revolved around angles, so let's quickly get to those before we go on to question 2. Right, so we were here at the inclination of AC. So we've got this little portion that we haven't done yet. And I'm specifically interested in the inclination of AC, because whenever you see that terminology, you go to the line, you draw the line, and you then find the angle that that line makes with the x-axis. And you agree with me? It does, that's the angle. Okay, so that will now be known as the inclination. And because there's no other angle on this diagram, I'm going to call that theta. That's the angle of inclination. Okay, so it's always draw the line that they've spoken to you about, and then find the x-axis, and the angle that that line makes with the x-axis is what we call the inclination. How inclined is that line to the x-axis? Okay, so the definition of inclination is that the tan of the inclination is equal to the gradient of the line in question. And tan theta is therefore equal to -2. Now, the only way we can find out what theta is if we use our calculator. So we're going to get a -2 into our tan. So we've got a -2 equals, and we've got an angle of -63. But you saw me drawing that line AC. That line AC has that sized angle. The -63 that the calculator gives you is the angle that's read in the opposite direction, so we don't want that angle. So we would therefore need to add on how many degrees? Yes, 180 in order to get the obtuse angle. So we now have 116,6 degrees. So it's 116,6 degrees is the inclination. That's how inclined that line is to the x-axis. So whenever an angle's obtuse, the calculator is always going to give you this angle. That's the angle read in the opposite direction. That would be -63. So we would just add 180 degrees in order to get this obtuse angle. Okay, so that's a quick revision on the inclination, midpoint, and equation of a line. Let's go on to the next question. We have a rhombus. So we talked about a parallelogram in the previous one. We talked about if you have two sets of parallel lines that aren't equal to each other, you actually get a trapezium. And now we've got this rhombus. Now, a rhombus is a very special kind of quadrilateral because it's got some very interesting properties. Okay, so we've got a rhombus. And we have its coordinates, A, C. And the diagonals of the rhombus bisect each other at M. And the point E is going to lie on BC. We're going to calculate the coordinates of M, and M is the point of bisection because they tell us that the diagonals bisect at M. So that point will bisect the diagonals, which means that this portion is equal to that portion, and this portion over here is equal to that portion over there. So we have, we've already established that those two pairs have been given, so it's easy for us to calculate the midpoint. We do that by adding up the coordinates. So 5 minus 3 is 2 divided by 2 is 1. And we get -4 plus 8 would be 4 divided by 2 is 2. So this midpoint M is 1, 2. Then we need to calculate the gradient of BC. This line BC, because E is lying on BC, the gradient of BC is the same as the gradient of EC. So the gradient of EC, change in Y, change in X. 1 plus 4, change in Y, change in X, 6 minus 5. So we get 5 divided by 1. The gradient of this line is 5. Now, because it's a rhombus, the parallelogram has got the same properties the rhombus has got the same property as a parallelogram. It's got pair of opposite sides parallel, or two pairs parallel. But the unique thing about this is we would like to find out when the adjacent pair of sides is equal, we would like to give it a new name. And so all four sides are equal would give it its definition of a rhombus. So the gradient of EC we've got, and now we know that because these lines are parallel, this gradient over here is also 5. Determine the equation of the line AD in the form y equals mx plus c. So we'd like to find the equation of this line over here. And we know with a straight line we need the gradient and we need a point. We have a point. Do we have the gradient? Can you see if I hadn't put these parallel sides on, we would not know that the gradient of AD is the same as the gradient of BC, because the lines AD and BC are parallel to each other, so they've got equal gradients. So that would be a reason. You could put it on the side, or you could say since AD is parallel, you've got the gradients must be the same. So we've therefore got the gradient. We've got a point. So we could certainly use that equation I showed you earlier, where it's y minus the y of the given point, and we give a negative 3/8. So it's plus 3 is equal to the gradient, which we worked out is 5, and x minus 8. And if you multiply that out, you would get y equals 5x, and you've got a negative 40 minus a 3 would be negative 43. And because this line has got such a steep gradient, it's going to cut the y-axis really, really low. So that kind of makes visual or intuitive sense there. Right, and then we would like to work out the size of theta, that is BAC, so they've defined it for us, and show all the calculations. So we would like to find the value of this angle over here. Just to show everybody where theta is, let's make it in green. There's theta, okay? How big is that angle, and how are we going to work that out? Well, can anyone tell me what the properties of the diagonals of a rhombus are? Okay, these diagonals do what the parallelogram does, which is they cut each other in half. But they do something else. Because all four sides are equal, you will find that it is only this unique shape where the diagonals cut each other perpendicularly. So we could actually talk about angle M1, 2, 3, and 4 as being the property of the parallelogram. And we could also work out that if that is 90, and all these angles are 90, how could we work out the size of that angle? And remember, when you're working with angles, you could be working with inclination, but you've also got a tool in mathematics that can help you to work out angles. What is that? Yes, trigonometry. Trigonometry is that powerful tool. And since I've got a right-angled triangle here, all I need is this length here, or that length there, it doesn't really matter, or that length there. As long as I've got one length in a right-angled triangle, I can use my trig. And so let's opt for AM, because we worked out what the coordinates of M are. And let's work out what that distance is. And we're going to do that down here. So we've got point A is a point negative 3,8. We've worked out that M is a point 1,2. So we can calculate its length. AM squared is equal to the change in y, so it's 8 minus 2 squared, and the change in x, which is 1 plus 3 all squared. So we get a value for the AM squared as 36 plus 4 squared, which is 16. So we get an AM squared of 52, giving us an AM of root 52. So I can go back onto the diagram and say that this length AM is root 52. So I've got angle, side, and so which other side could we use? Could we use BM, or could we use BA? Well, I don't think we've got more information. I don't think we've got B, so we've already got the length of C. So we could say that CM is also root 52. And we also know that one thing that we haven't discussed yet is that the rhombus's diagonals will bisect the vertex angles, so that this angle over here is also theta. And so we've got another right angle triangle over here, which is going to be congruent to this triangle here, and those two triangles are going to be congruent as well. Right, so we've got a choice. Let's just fill this in, root 52, of going to either find the coordinates of D, so we can have another length to work with, or we can find the coordinates of B, so we can have this length to work with. Because the only way we can work with trig is if we've got two sides, not just one. So we need, if we're going to find that angle, we are going to require two different sides. So let's see if we can work out the coordinates of D. We did this before. We've got M's values are 1, 2, and we would like to find what the coordinates of D were. And we've got the equation of AD as well. And we've got the equation, or could we find the equation of CD? And I think, yeah, I think we're going to take a break there and see if we can find some more information during the break.
Right, thank you so much, Dina. Mina, as you're about to take that break, I have two comments. One is from Msovo Makamu Kanza, our usual suspect on the page. During Mondays on our Triple M's. She says, Mina, you're doing a great job for me and others. We are glad to have you. You're such a wonderful teacher and a teachful teacher like you. That is so wonderful. And the last one, I just want to acknowledge Bafana Househead Mathangu. You've been doing great over the page, helping other mindsetters. Keep up the great work, dude. We like what you're doing. So mindsetters, we'll see you after the break. To tell you also more about Curio, we'll also be having some instructions over our Facebook page. So make sure that you get over there. Your code is M11. So make sure that you jump over, mix it too, because we're learning and also we are on the social networks. See you after this. Welcome back, pre-matriculants. I hope you're enjoying the show as much as we do. Me and Mina are having such a great time. It is our Triple M Day, Mindsetters Maths Monday, and of course, edit the M there, which is for Mina. So Mindsetters, get over our Facebook page. It is facebook.com/learnextra, and make sure that you are there to participate with us. Share your news, share your questions, and let's help one another. That's how we roll on Learn Extra. Mina, take your time.
Thank you very much, Abraham. We did get a question about where analytical geometry is situated, and it is in paper 2. It is not found in paper 1, it is paper 2. So we were busy trying to calculate an angle theta, and I was trying to integrate trigonometry into the question, but there wasn't sufficient information. So let's go back and just give you a route to actually get to that answer. Okay, so we did work this length out. We also know that the diagonals of a rhombus, they will bisect the angles. So this angle here will be the same as that angle there. And I think the best way, because we don't have another length, is to maybe just try and work with the inclination of the lines that we do have. So we have this diagonal, which makes this angle. I'm going to call that beta. And we've got this line here, BC, and it makes this angle, and we're going to call this alpha. So we've got these lines creating those angles. Can you see that if we work with that angle, we are able to find a little quad over here, even a quad there, it doesn't really matter. But if we worked with this quad here, we would have two angles and a 90, so we could find out that angle, and then we could work backwards into that triangle there. So, or just work with this angle here, which would be the same as that angle because they're alternate angles. It doesn't matter. There are many routes to this. Okay, but let's take that the gradient of AC, which has already been worked out here. Here's the gradient of AC. It's negative 3 over 2. Remember what we said earlier about the inclination. The definition of the inclination is that the line that you're working with will make an angle with the x-axis, with the positive direction of the x-axis. And that whole angle is what we call the inclination. So let's work with the calculator and see what that angle is. Let's just first write down the information. So we've got tan of beta is equal to negative 3 over 2. And we've got tan of alpha is equal to 5. Remember, that was the line that we worked out first. So our calculator will give us what those angles are. We've got the angle giving us negative 3 divided by 2, which is negative 56. Remember, we said earlier, if it's a negative angle, an inclination is always positive. So it's going to be plus 180, which gives us 123,7. So it's 123 is 123,7 degrees, because inclination is always defined as a positive angle. Now, interesting to remember is that if your gradient is negative, so if m is negative, then that means that the inclination is obtuse. Okay, it's just good to know that. But your calculator, obtuse. Can't spell this afternoon. So we've got obtuse. And if we have a positive gradient, then the inclination is going to, in this case, always be acute. So we can refer back to the way that the line is making that angle with the axis. So acute angle it's making with the axis, and this line is making an obtuse angle with the axis. Okay, tan alpha being 5. Let's see what the calculator shares with us about that. Let's clear, find the angle that gives us 5. We're expecting it to be acute because it's positive. So let's see, 78,7. So alpha is 78,7. Okay, so we have successfully been able to establish that this angle and that angle would give us that. We would actually need to get this obtuse angle here, this angle here, and let's go and calculate that. So the supplement of alpha would be whatever we had there, minus 180, which would give us 101,3. So that would be 101,3 degrees. So together, these two angles, plus our 90, so this angle, and this one, would be in a quadrilateral. So we would get, in the quad, we would have 123,7 plus our 101,3 plus 90 degrees would equal to the sum of the three angles. So the remaining angle, which is our, we've defined it as x, would be 360 minus that. So let's go in here and say 360 minus our 123.7 minus 101.3 minus 90 equals. It is actually 45 degrees. So that actually gives us 315 degrees. So our remaining angle is 45. Okay, let's see how that helps us on our diagram. We've got x is now 45 degrees. So if this is 45 degrees, this angle here, it means that this theta that we were originally looking for, because the question was really looking for theta, and that's BAC, would actually be 45 because that angle is already 90. So we can write it off by saying, therefore, BAC is 45 degrees. Okay, so the trigonometry in this case didn't really help us. We were missing some lengths, and so we had to find an alternative route of being able to get to this. Right, and the last question. What are we dealing with? Oh, with a rectangle. So we've looked at the parallelogram, we've looked at its properties, we've discussed the property of a trapezium, and we've looked at the rhombus. And the most important thing about the rhombus, let's write it down so that you can accompany me with that, would be the real difference between a rhombus and a parallelogram is its diagonals. So I can find three things about the diagonals of a rhombus. The diagonals they bisect each other, just like our parallelogram. They're perpendicular to each other, or they bisect perpendicularly, and they bisect the vertex angles. So these would be the property of the diagonals of a rhombus, and then a property that would not be the same as your parallelogram would be all sides are equal in length. Okay, now if we take this further, if we take these ideas further, and we take all this, and we say, I want to keep all those properties, but I also want my diagonals to be equal. So take a rhombus and then make its diagonals equal. What do we get? So take a rhombus, plus you make the diagonals equal, you get a square. Okay, so there is a connection between a rhombus and a square. They're specialized kinds of quadrilaterals. In the square, it takes on all the properties of the rhombus, plus an additional one, you just make the diagonals equal. Okay, right, but we're working with a rectangle. So let's get back and see what we can do with this rectangle. So we've got PQRS is a rectangle. Now, how would you define a rectangle? We know that if we start with a parallelogram, how could we change the properties of a parallelogram to make it into a rectangle? Well, you know the parallelogram has got those sides that are parallel, but its vertex angles can be doing anything. If you had to change those sides all the way until you got to a unique position, and that position was that those sides were perpendicular to each other, now you've got a rectangle. So a rectangle is a special kind of parallelogram. It's, let's write it down as well. So if we take so if we take everything we know about a parallelogram, if we had to start with a parallelogram, and we add on that the sides are perpendicular to each other, then together this gives us a rectangle. And now the beauty of this is that a rectangle, if you're going to do that, so if you're going to take your parallelogram, okay, and all you do is you now rotate these sides so that they're perpendicular to each other. then you've created a rectangle, but you've done something else. You've now also created that these diagonals are equal. So a rectangle's property is that its diagonals are equal. Okay. So if the diagonals are equal, but they don't bisect each other, you would have to make these two sides the same. So you've actually got to make those adjacent sides equal. Then you're going to have your square. So a rectangle is not a square because it doesn't have its diagonals bisecting at 90 degrees. Okay, so this is a very simple way of being able to categorize those various quadrilaterals. Okay, let's go back and let's see what we are doing here. Show that A is equal to 4. So we are given a rectangle with these vertices P, R, Q, and we also given S, and we would like to know what the value of A is. Now, grade 11s, I want you to look carefully. You've got this line, because it's a rectangle, and you've got this line. These two sides are perpendicular to each other. And something we haven't looked at yet during today's lesson is that lines that are perpendicular have got something special happening with their gradient. So the gradient of PQ multiplied by the gradient of QR. So we've got gradient of PQ multiplied by the gradient of QR is always going to give me -1. So I could set up that equation, and I'm going to do it on the side here, that if I take A minus 0, which is just A, divided by 4 plus 4, which is 8, and I multiply it by the gradient A minus 0, which is A, over 4 minus 6, which is -2, then I'm going to get -1 because my lines are perpendicular. And somewhere I must say, since PQ is perpendicular to QR. Okay? So I've got my A squared is equal to a 16. So A can be both positive and -4. Now, since Q is in the first quadrant, it can't be -4, so A must be obviously 4. So there's my Q. So I've been able to show that A is 4. Notice that I have not created a circular argument. As you go into grade 11 and 12, you'll need to be showing some values. We don't take the values and insert them into the question. Basically, that's like the answer to the question, and you need to work, calculate, analyze, do whatever you need to do to arrive at the answer. Okay. Determine the equation of the straight line that passes through the points S and R, and it's in that form. And then we've got to calculate the coordinates of S, and we've got to also find the length of PR. Okay, let's see if we can work out what the coordinates of S are. We've got that this gradient over here is going to be the same because these lines are parallel. We've got that these lines here are also parallel, so their gradients are the same. And I think that I'll give you some tips on how to find S. Once you've got the equation of PS, which you can work out with that gradient, and the gradient of SR, which you can work out with PQ's gradient, then you can find the equation of both lines, point of intersection, find out S, find out the coordinates of S, and then the last question is you need to translate that triangle, that figure, right and up in order to get the figure in quadrant 1. So I'll leave you to play around with those last few questions. Have a good evening.
Thank you so much, Mina. Mindsetters, thank you to you too for tuning in. And a big thank you also to our sponsor, Macmillan. Make sure that you do check out their ebooks. I've posted a link on our Facebook page. But otherwise, it's been a great evening. And Mindsetters, you always rock big time. Big ups to you. Thank you.